Welcome to Electrical Engineering 362 Electromechanical Energy Conversion. This is Module 1, Lecture 2, Single and Three-Phase AC Circuits. In this lecture, we will discuss the phasor analysis of parallel and series circuits, focusing on the two types of RL circuits, one series and one parallel. We will show how to perform real and reactive power calculations using phasors and introduce the power phasor diagram. We will also be introducing power factor and trying to provide some physical meaning for that. And then we will introduce three-phase systems and compare time-variant scalar and time-invariant phasor representations of three-phase systems. We will discuss Y and delta connected loads in three-phase systems and show how to derive a single-phase equivalent circuit for a three-phase system. So in the last lecture, we focused on the parallel resistive inductive load, where we had a single inductor and a single resistor in parallel. And we showed that we could analyze this circuit, or our aim in analyzing the circuit is to find the current that is going to the load for a given voltage. And we found that current by performing Kirchhoff's current law as it applies to this circuit, recognizing that we would have a current going down this branch, which was purely inductive, would therefore line up along the imaginary axis, and then we would have a current in this branch, which, to be completely general, I'm showing as a phasor, even though it will have a phase angle of 0, and so we showed using the phasor diagram that if we found the current in the resistive branch by dividing the RMS voltage by the resistance, and then found the current in this inductive branch by dividing the RMS voltage by the inductive reactance, we would have two phasors, and we can add them together and find the total phasor representation of that current. Now let's consider taking a resistor and an inductor and putting them in series. What would be our approach here? Well, it would be very different. The way that we would want to approach this is to look at the combined impedance of the load and use that impedance to find the current. So quite simply, I is equal to whatever the voltage is divided by the impedance. So what is the impedance of the RL load? Well, the impedance in phasor form is going to have this representation. It's going to have a magnitude and it's going to have an angle. So it's there's a magnitude of Z and a Z phase angle. Now, something I didn't point out in the last lecture, and we could go back and look at this parallel circuit because it certainly applies here in the same way. If we knew what this impedance was looking in here, then we could find the power factor angle from the impedance angle. Essentially, the angle of the impedance, which is phi z, is equal to the negative of the power factor angle. This will become a little clearer as we look at this series RL circuit. So first of all, when we combine the impedance of the R and the impedance associated with the inductor, and that reactive impedance is JXL, we would have the Z represented as R plus JXL. So the magnitude of Z is equal to the R squared plus XL squared. And the angle of phi z of Z is the inverse tangent of the imaginary part XL over the real part. So I've just rewritten these three equations here, being a little bit redundant. But it's that simple. Now, if we look at this, we can see why phi z is equal to the negative of the phi power factor. So another way of one way to find the current from this is to, let's say we started with this and we didn't have the impedance figured out. We would have to do dividing this RMS quantity here by a complex impedance. How do you do that? Well, you have to find the magnitude of that current phasor, and you have to find the angle of that current phasor. We already know that the magnitude of the current phasor is going to be IRMS, and the angle of the current phasor is the power factor angle. So in order to divide a single quantity, this is just a single number, VRMS, we have to divide it by the magnitude to get this magnitude term here, the magnitude of the impedance, which we showed in the last slide is R squared plus XL squared. And then we have to find the angle of the current this way. Now if we recognize that what we actually have done here is we have calculated the current by taking VRMS and dividing it by the impedance. So we have the amplitude of the impedance and we have the angle of the impedance, which is phi z. So moving the angle from the denominator into the numerator to find this current expression, we have VRMS over the amplitude z, and then to get it, the angle on the top here, it becomes a negative angle. So what have we just done here? What we've done is we're saying that for any AC circuit, find the load impedance, divide the applied voltage by that impedance, and that gives you the current. So I is V over Z. In the case that we're showing, where we are saying that the voltage has a angular reference of 0, then we have VRMS, the RMS voltage, divided by the magnitude Z and the phase Z. That's equal to VRMS over Z, with an angle, a phase angle of negative phi Z. Now these quantities that we're showing is, first of all, what is this? Well, that is the RMS current. IRMS is VRMS divided by the amplitude Z. And what is this? Well, remember, that's the power factor angle. So the power factor angle is equal to the negative of the impedance. I want to go back here and I want to highlight this term here. We've talked about power factor angle, but what really is power factor angle? Why do we call it a power factor angle? Well, because it's associated with a term that we call power factor. And it will become a little bit clearer as we proceed what that is and why it's important. But as we state right here, this power factor is the cosine of the power factor angle. So often what we will do is we will define a load by its current or its power and a power factor. For example, we might say that a load has 0.8 lagging power factor. So it's important that we stipulate whether it is leading or lagging, because the number of the power factor, which is cosine of the power factor angle, doesn't tell us anything about the sign. Whether we say it is leading or lagging, it tells us. So if it's lagging, then we know that the angle is less than 0. If it's leading, the angle is greater than 0. So how about phasor diagrams? How would we approach developing a phasor diagram, and how might it be useful to us for this type of circuit where we have a series RL? So instead of doing KCL to develop the phasor diagram, we instead would apply Kirchhoff's voltage law around the loop, and that would mean that we would have phasor representations of the input voltage, the voltage across the resistor, and the voltage across the inductive reactance. So in the phasor representation, the source voltage is on the real axis, just as before. Now, in order to find these other two voltage drops here, we have to know what the current is. So we'd have to say I is equal to the voltage divided by the impedance. And once we do that, we know the amplitude of that current, which is this IRMS, and we know the phase of that current, which is the power factor angle. So the voltage drop across the resistor is pretty straightforward. We would simply multiply this current times that number for R. So it actually, we would just scale the magnitude of the phasor according to R. And that's the voltage VR. Now the voltage across the reactor is a little bit more tricky because we have a reactive component involved. So what is the voltage across the reactor? It's going to be JXL, just as I'm showing down here, times the current phasor. Now what we have is XL is just a scalar number that we would multiply times I, and the amplitude would scale accordingly. But what J does is it changes the phase shift. And the easiest way to think about it is that J represents a 90-degree phase shift in the positive direction. So we have, by convention, defined the angular movement being positive in this direction, because what we're showing here obviously is a negative power factor angle. It's going the other direction. So if you look at, for example, a real axis, the imaginary axis is 90 degrees shifted in this direction. So it's J times whatever's on the real axis would put you here. We can do the same thing. Try to explain this. We've defined the power factor angle, so we really know that there's an axis along which the current is lying, the phase current. 90 degrees shifted from that axis, we create another axis. So this axis, I could say, here's the I axis, and this axis here is the JI axis. So then if we think of it that way, then we can look at this term here and say that really what we're doing is just saying XL times JI. So you take this current here and rotate it 90 degrees. It's right there now. That's JI, and then you scale it, multiply it by X, get it to the right let's try to get it here to the right amplitude by multiplying it times X. Move it over here to the end. We're adding up the voltage across the resistor and the voltage across the inductor, the RMS phasor voltage. That would tell us this is the input voltage here. Another way is, we already knew what this, so if, for example, if you didn't know what VRMS was, but you knew what the load impedance was, and you knew what the current was in amplitude and phase, you could find the voltage by adding these two phasors together, and the point here, drawing a line from the origin, ends up right along the real axis. Another way to look at this is you say, oh well, I'm just adding this voltage plus that voltage, and if I shift the sign here, what I've done is I've summed the three voltages to 0. That's the same as saying that what I just did here was said V input equals VR plus VXL, and now I'm going to say that I know that around any loop the voltage has to sum to 0. So what I really have said is VR plus VXL minus V equals 0, and that's what I just did. Now that's a little bit of a trivial example, maybe not a useful one, but we will find that these phasor diagrams can be very useful to us in the future.